Welcome everyone to a new episode of the Shannon channel. I'm really happy today to have Nihar from CMU, and he's going to talk about a topic that I'm really excited to hear more about because I think it involves all of us in academia, which is the peer review. Thanks again, Nihar. So we're all looking forward to your talk today.
Yeah, thank you so much, Salim and Sergey, for inviting me and hosting me. So I'm going to talk about problems and solutions in peer reviews, something that in our group we have been working on since the last couple of years. Before I start out, something very important, please feel free to interrupt if any of you have any questions. So peer review, especially in say machine learning and AI venues, is under tremendous strain. There are several thousands of submissions and there is an exponential increase year by year. And it's not just in AI or ML. Peer review is a challenge in broadly many disciplines in science and engineering. For example, in this very nice article in Nature, Rennie says that peer review is a human system. And so everyone involved has prejudices, misunderstandings, there are biases, inefficiencies, there is some corruption, and all in all, the article says that peer review is unscientific. And survey after survey after survey of researchers in a wide variety of different scientific fields indicates an overwhelming desire for improving peer review. So with this motivation, the goal in our research is to tackle the systematic challenges or demons that exist in peer review using principled and practical approaches. So we frequently take a theoretical perspective, establish the foundations, and also we strongly look to make real world impact. And we are already making real world impact. In this talk, I'm going to discuss 5 issues in peer review. And you can also treat this as an outline of the talk. I'm going to go into the first issue of subjectivity in detail. I'm going to discuss miscalibration in some detail after that. And finally, for biases, noise, and strategic behavior, I'll provide a brief overview. And I'll be very happy to chat offline about any of these. Again, please feel free to interrupt if you have any questions throughout the talk. So let's start with subjectivity. And this is joint work with Ritesh Nuthigattu and Arial Procaccia. So it's well known that different reviewers have different subjective opinions of how to weigh different criteria when making a decision. As an example, let's say this green reviewer thinks that novelty is not really useful unless the paper improves upon the state of art by at least 10%. On the other hand, let's say all of these blue reviewers think, or which is everyone else, thinks that, hey, novelty is extremely important because in the long term, it can lead to major breakthroughs. So let's say if a paper comes along which has really novel ideas, but has only a moderate improvement over the state of the art, the green reviewer will reject the paper, whereas most other reviewers would have accepted this paper. So you see that this is kind of unfair because the final decision of that paper is very strongly dependent on a subjective preference of that particular reviewer about something that's extrinsic to the paper, about whether novelty is more important or whether improving by 10% is more important. And this issue is very well recognized in the literature. Question? Okay. This issue is very well recognized in the literature. It's also often called a commensuration bias in peer review. And recognizing this issue, we take a computational approach to this and ask the question, how do we ensure that every paper is judged by the same yardstick? And of course, we want it to be a good yardstick. So here's a more formal description of the problem setting and some notation. So we consider a setting where when a reviewer reviews a paper, the reviewer is asked to judge the paper on some K pre-specified criteria. These criteria could be things like originality, relevance, significance, etc. The reviewer is also asked to provide an overall score for the paper. In terms of concrete notation, if a reviewer I reviews paper J, the reviewer gives a vector xij, which we call a criteria score vector. So xij is a vector of length k, representing the scores given by reviewer I to paper J for the k criteria. The reviewer also gives a scalar yij to paper J. This is the overall score. Yij is the overall score. Now, for simplicity, we'll assume that all the scores lie in the interval 0 to 1. So I'll ask you to remember these three pieces of notation: K criteria, Xij is the criteria score vector, and Yij is the overall score scalar. Now, we make this assumption that every reviewer implicitly in their mind has some mapping from the criteria scores to the overall scores. We assume that this mapping is coordinate-wise non-decreasing. That is, for example, if the significance score goes up, but all other criteria scores remain the same, then the overall score should not go down. Each reviewer has their own such mapping, and different reviewers can have arbitrarily different mappings. So we only assume coordinate-wise monotonicity. Any questions? Okay.
I think so far so good.
Yeah. Great, thank you. Now, in terms of this notation and terminology, we wanted a common yardstick for all papers. And in terms of this notation and terminology, we'll say that we need to get a common mapping for all papers, a common mapping from criteria scores to overall scores. Yeah. So it is this subjective mapping, criteria scores to the overall scores, that we are trying to fix. We want to remove the subjectivity in this mapping. So our approach is data driven, that is to learn a mapping. And here is what we do. So first we obtain all the reviews. So any review comprises of the criteria score vector and the overall score. We get the data. And now from this data, we learn a mapping. So mapping, as I said, is a function from the criteria scores to the overall scores. And we will learn some mapping, which we will call f hat from this data. And then now that we have a mapping, we will use this as a common mapping for all the reviews. So for every review, reviewer I paper J, either replace or augment the overall score Yij, which was originally given by that reviewer, with f hat of Xij. So Yij was the overall score computed by that reviewer based on that reviewer's personal mapping. And we say that, hey, instead, let's try to use this learned mapping f hat. F hat kind of represents a common community consensus on the mapping. And we apply this f hat to the criteria score Xij in that review and use f hat of Xij. So this is the higher level approach. And the key question here is obviously, how do we learn this mapping? Now, here's the framework that we follow. For simplicity.
Excuse me, Nihar.
Yes, question.
This F, do you assume to be universal across all reviewers?
Yes, so the mapping, we are going to learn a common mapping, a single mapping across all reviewers.
Okay, thank you.
Just to clarify, like, you could extend this to say that for the theory, people will learn one mapping, and for the applied reviewers will learn another mapping, and so on. Those are simpler extensions, but here we are going to assume a single mapping. across everyone. Great, thank you for the question.
So Nihar, just also to
yeah.
understand more the models. So you assume that each reviewer has different weights for the different criteria, but you want to learn an average weight? Is this right?
Yes. So just to clarify, we won't assume weights. We are not assuming something linear. So they have some coordinate-wise non-decreasing function. So everyone has a function, and we're going to learn a function which is in some sense a consensus of all of them.
Okay.
Now I'll define in a minute what I mean by that. Like it'll be clear in the next few slides.
Okay.
Yeah. Great. Other questions? Please ask. Okay. So here's the framework that we'll use for learning this mapping. So for this talk, for simplicity of presentation, I'm going to assume that all papers are reviewed by all reviewers. Now the algorithms we design are more general. They can handle arbitrary subsets, and as I'll discuss later, we have also tried it on real conference review data. Okay, for this talk, for simplicity, we'll still assume everyone reviews everything. Now the data that we have, we write it down as two matrices: the matrix of criteria scores and matrix of overall scores. So both these matrices have reviewers as rows and papers as columns. The ijth entry of criteria score matrix is xij, that is a vector of length k, which represents the criteria scores given by reviewer I to paper j. The ijth entry of the overall score matrix is the overall score given by reviewer I to paper j. That's yij. This is the data that we have. Now, for a moment, consider an ideal world where there is no subjectivity, nothing. All reviewers are exactly identical and everyone's on the same page and so on. In that case, you might have a common function f across everybody such that f, when applied to any criteria score entry, results in the corresponding overall score in the data. This is an ideal world. And of course, the challenge that we are dealing with is that the world is not ideal. The challenge is that different reviewers have different mappings. And so what do we do? Well, inspired by empirical risk minimization, we try to find the function f that best approximates this ideal world. Specifically, we learn this mapping, which we call f hat, which is the argmin over some function class script f that I'll define in a minute, of an LPQ norm, which again I'll define in a minute, different LPQ norm loss of the difference between f of the criteria score matrix and the overall score matrix. So this is inspired by standard empirical risk minimization. And what I do need to specify now is what is this function class script f and what is this loss. So the functions class script f, we simply assume it's the set of all coordinate-wise non-decreasing functions. So again, in any function in this set, if let's say the criteria score for significance increases, everything else remains the same, then the overall score does not go down. So coordinate-wise non-decreasing. We make no other assumptions on script f. So there is no linearity, no convexity, no Lipschitzness, continuity, etc. Okay. Now I need to specify the loss here. And as you would know, the choice of the loss function in learning is an important choice. And towards this, we consider this very general class of norms called the LPQ norms. So in case you are not already familiar with LPQ norms, it's a natural matrix extension of the standard vector LP norm. The LPQ norm is associated to two parameters, P and Q, both in the range 1 through infinity. And the LPQ norm of a matrix is computed as follows. So let's say if we have this matrix, from the previous slide. Then you take the first row, which is a vector, and compute its LP norm. So this LP norm is the usual vector LP norm. Now take the second row and compute the LP norm, and so on. So for every row, you compute the LP norm. Now you have a vector of LP norms represented by the asterisks here, and you take the LQ norm of this vector. And the result is the LPQ norm of this underlying matrix. So this is the class of LPQ norms, where P and Q can take any values from 1 through infinity. Now, some of you might be familiar with these. LPQ norms are used in a variety of different applications in many different fields. But now, if you look at the various papers that use LPQ norms, they choose different values of P and Q for the various different applications. And many of these papers provide some justifications towards why they made that particular choice. However, these justifications are usually quite heuristic in nature. However, given the importance of the choice of the loss function in learning, here we want to take a principled approach towards choosing this loss function for our empirical risk minimization. And so the key question that we ask here is, which loss function should we use in the minimizer on the previous slide? Any questions? Please ask. Okay, please feel free to interrupt at any point. Just unmute yourself and please ask if you have questions. Okay, so towards understanding this, towards addressing this issue, we take an axiomatic approach. So axiomatic approaches are far more popular in economics and social choice theory, although as some of you might be familiar, axiomatic approaches are used in various other fields as well. So in an axiomatic approach, what is done is, first, for the problem that we are dealing with, we'll identify certain special case scenarios that will be easy for us humans to reason about. And now, under those special case scenarios, we will establish certain necessary conditions, or what are called axioms, that we will need the solution to satisfy. And through these necessary conditions, the goal is to try to narrow down the space of possible solutions in order to try to pick one solution in a more principled approach. Now, the special case scenario that we will consider for our problem setting is as follows. We will consider the special case where each paper gets the same criteria scores for all reviewers. So for example, for paper 1, X11 was the criteria score it received from reviewer 1. X21 was the criteria score it received from reviewer 2, and so on. And the special case is when X11 equals X21 equals X31, and so on. So all the criteria scores given by all reviewers for paper 1 are identical. Likewise, for paper 2, we will consider the special case where X12 equals X22, and so on. So this is the special case we'll consider. Now, in this special case, we'll slightly simplify notation to make our life easier. So for paper 1, since the criteria scores for all reviewers are the same, the reviewer subscript is irrelevant. And so we will just denote the criteria score received by paper 1 from any reviewer simply as X1. Likewise, we will let X2 denote the criteria score vector received by paper 2 from all of the reviewers. Any questions? Please ask.
So it's like you have one reviewer here.
They might give different overall scores.
Ah, okay.
So that's a very good point. So each reviewer has their own subjective mapping through which they'll compute a possibly different overall score. Yeah, that's a great question. Thanks. Other questions? All right. So now let's focus on this specific special case. And now under this special case, we'll establish 3 necessary conditions or axioms that I'll argue are quite natural. The first axiom is what we call consensus. And this axiom says the following. So let's say there is some vector x and some scalar y, such that you see in the data that every reviewer has mapped x to y. Then you want your learned mapping f hat to also respect this mapping. That is, you want f hat of x to be equal to y. The second axiom is what we call dominance. I'll describe this informally here, and I'll go into more details of it in a couple of slides from now. So informally, dominance says that suppose there are 2 papers, say A and B. And suppose we all happen to be in agreement, looking at the scores received by the 2 papers, that paper A is at least as good as paper B. Then we want the learned mapping f hat to also satisfy that. That is, we want f hat of xa to be at least as much as f hat of xb. Any questions?
Nihar, so this axiomatic approach, what is the goal of this? Is it to like restrict your class of functions?
That's correct. Or the class of loss functions. Yes, that's correct.
You mean the class of loss functions, the LPQ functions, or the class of functions in general that you're
right. So the class of that's a good point. So the class the class of function script f, we just assume it's a coordinate-wise monotonic set of all coordinate-wise monotonic functions. So that's fixed. Now what we want to do is we will restrict the class of loss functions, which will implicitly restrict the learning algorithms that can be used. Right? It's a smaller class of loss functions means a smaller set of possible learning algorithms, and which then implies that if you have some particular data, then the possible f hats that you get for that data, that's also restricted. So we are not explicitly restricting f hat in any way. We are just trying to narrow down on what loss function we want to use in the LPQ space.
Okay, thank you.
Great. Other questions? Please ask. Great. So the third axiom is what we call strategy proofness. And the formal statement is here, and it's a bit of a mouthful. So let me tell you the higher level picture of what this strategy proofness is saying. So now suppose I'm a reviewer and I know that you're going to learn a mapping, and this learned mapping is going to be considered as the community's preference of how to weigh different criteria. This learned mapping is also perhaps going to be applied to the various papers, used wherever, and so on. Then what I would personally like is that this learned mapping should be closer to my own personal mapping, right? If I have a very high preference on theory, then I would be really happy if the community consensus is also that theory is great, right? Theory has to be high weight. Now, in order to attain that, now I'm giving these overall score to these papers, and I could manipulate them. What this axiom says is that if a reviewer tries to manipulate the overall scores that they are giving, then for any kind of such manipulation, the learned mapping cannot be brought closer to their own mapping. And that's what we call strategy proofness. No reviewer can strategically manipulate the scores that they give to try to bring the learned mapping close to their own mapping. Any questions?
So Nihar, this is kind of like low influence, like voting. Like I cannot choose my vote but here you're kind of forbidding it, like from even moving a small epsilon, right? Even that small epsilon you forbid it.
Yes, so we forbid moving a small epsilon by incorrectly reporting your y's. So it's like you have to report. So the best thing for you to do as a reviewer is to report truthfully.
Okay.
If you misreport, then it can only hurt you.
Okay.
So just to give a higher level context, strategy proofness is very well studied in the literature on voting, as you were pointing out, where the goal is to design a voting rule such that if I have a certain preference over the candidates, then it is in my best interest to correctly specify that preference. If I specify some other preference, I cannot get a better outcome. Now, in the voting literature, for this issue of strategy proofness, there are mostly negative results. That is, whatever you do, there will be a way in which the voter can manipulate and gain a better outcome. So you have the foundational Gilbert-Satterthwaite theorem, and there's a lot more literature.
Do you allow here reviewers to collude, or that's kind of not something like maybe?
No, we are not looking at collusions. Like that would be even much more stronger requirement. Yeah, we are not looking at that at this point. Yeah. Great. Other questions? Okay, so we put forward these three axioms: consensus, dominance, and strategy proofness. And with these three axioms, our goal is to narrow down the solution space, that is, narrow down the possible loss functions that we can use. The hope is that we can have a small enough set in which we can pick one in at least a more principled manner. Now, we show that in fact, these three axioms narrows it down sufficiently enough that there is exactly one choice that remains. That is, setting P equals Q equals 1 is the only choice that satisfies these three axioms. The good thing is there is at least one such loss which satisfies these axioms. And what this means is that if you are happy with these three axioms, and then this is the only loss function that you can use under this framework. Another positive is that, as I was mentioning, the classical voting literature is riddled with negative results, Gilbert-Satterthwaite or Arrow's theorem, and so on. Whereas here we do get a positive result, and a concrete one in the sense there is exactly one solution. Now, in terms of the only if part, it turns out that strategy proofness axiom is violated when Q is greater than 1. Now, this is closely related to the well-known fact that medians are strategy proofs, but other LP vector norms are not. Consensus is violated when P is infinity and Q is 1. And dominance is violated for the rest of the parameters. And in the next slide, I'd like to focus on this part about dominance for two reasons. One is that I'm yet to define what this dominance means. And second, because at least me and my co-authors found this result to be quite paradoxical. So before I go into details, I'll pause here for any questions.
So Nihar, for the strategy proofness, is there what would be the strategy for Q that is strictly greater than 1? Is this interesting? Like,
that's kind of standardish. At least we use standard tools where like standard tools from much simpler problems on just LP or LQ norms being strategy proof or not.
So the reviewer can. So the reviewer can bias the overall review towards it. Okay.
That's correct. Yes. Yes. Those are simple enough to describe offline, not enough. Okay. I guess not that simple enough to describe in the talk. Okay. Other questions? Please ask. All right, so let's go into more details of dominance. Now, I'm going to talk about dominance, and I'm also going to put you folks in the spot a couple of times. I'm going to ask you a couple of questions on this slide. So I'll try to make it more interactive over Zoom. Let's see how it goes. So we said that there's a wider range of parameters for which dominance is violated. And in this slide, I'll illustrate it with a specific choice of P and Q. That is, P equals 2 and Q equals 1. So we have this L21 loss. Now towards this, let's consider the simple setting where there are 2 papers, 3 reviewers, and K equals 2. That is, there are 2 criteria. Now let's suppose that the criteria scores received by paper 1 from all reviewers is X1, which is 1/4, 3/4. Okay. So all reviewers give paper 1 the same criteria score vector, which is 1/4, 3/4. And for paper 2, all reviewers give the criteria score vector X2, which is 3/4, 1/4. You see, they're symmetric. Now let's say here are the overall scores received by the 2 papers from the reviewers. Reviewer 1 does not like either paper, gives 0 to both. Reviewer 2 gives a score of 1 to paper 1 and a score of 0 to paper 2. Reviewer 3 gives a score of 0 to paper 1 and some z, which is strictly smaller than 1 to paper 2. Now let me ask you folks a question. Suppose you were the program chair of this conference, and let's say this is the only information that you have, you know nothing else. Now your goal is to pick one of the 2 papers as a better paper. Which of the 2 would you pick? Feel free to unmute yourself.
I guess paper 1.
Great, paper 1. We have a few people saying paper 1. Anyone for paper 2?
Yeah, I think I'm for paper 1. But I feel like there's a trick here.
No, it's not a trick. Okay. So a lot of us think paper 1, where all the votes so far were on paper 1, and it seems intuitive, right? That the criteria scores are symmetric, and suppose for a moment z was equal to 1, then everything about the 2 papers is symmetric, so they are the same. But now by making z strictly smaller than 1, we've made paper 2 worse, and hence paper 1 is better than paper 2. So in this axiom, under this condition, what we want is that we agree that paper 1 is better than paper 2, and hence we want the learned mapping f hat to respect that. So we want f hat of x1 to be at least as much as f hat of x2. Okay, so now let's see what happens when you try to learn under this L21 loss. Now this L21 loss has a very cool connection to the Fermat point of a triangle. So what's a Fermat point of a triangle? So if you have a triangle, you find the point such that if you take that point and then compute the Euclidean distance from that point to all 3 vertices of the triangle, add up these 3 Euclidean distances, then that total Euclidean distance should be as small as possible. So the Fermat point of a triangle is the point which minimizes or which has the smallest total Euclidean distance from the 3 vertices. Okay. Now, what's the connection with the L21 loss? Well, that's a very nice connection. So here in L21, we have P equals 2, and that exactly corresponds to the Euclidean distance. We also have L21, in L21 we have Q equals 1, and that exactly corresponds to adding up the Euclidean distances, right? Just the L1 now. So now this says, and this implies, and there's an easy proof, that f hat x1, f hat x2, that is the learned mapping when applied to x1 and x2, that is exactly the Fermat point of the triangle shown here. The three vertices of the triangle are just the three rows of the table on the left. So one vertex of the triangle corresponds to reviewer 1, who gave score 0, 0. The second vertex is 1, 0, and the third vertex is 0, z. Yeah. And this is not hard to show using the intuition that I just mentioned to you. All right. So now these are the three scores given by the three reviewers. And now suppose z was equal to 1. Then the Fermat point of this triangle can be computed to be exactly 0.2, 0.2. So it's symmetric as we expect. There's nothing surprising here. But now let's say we take the vertex on top and move it down. We don't do anything to anything else. Just take the above vertex and move it down. Are there any guesses where the Fermat point will move? Please feel free to unmute and just give a wild guess.
We'll move to the right down.
We'll move to the right down. Thank you. Any other guesses? Okay. So it turns out counterintuitively, at least highly counterintuitive to what I had initially thought, it moves far more to the left and then down. And so the Fermat point is when z equals half is in fact 0.12, 0.15. So since f hat x1, f hat x2 corresponds to this Fermat point, we have that f hat of x1 is strictly smaller than f hat of x2. And this counters what we wanted on the left-hand side. So here we considered this L21 loss. Now, this L21 loss is violated. And by the way, so the L21 loss is actually a very intuitive loss to use. So when you're taking p equals 2, you're just taking the L2 norm error of each row. That is the L2 error corresponding to every reviewer. And then q equals to 1 just adds these errors up. So L21 loss is a very intuitive loss. And for this intuitive loss, as we have seen for this simple example, it breaks down. The proof for general LPQ is much more involved, but uses the same kinds of ideas. Any questions?
Nihar, can you please explain what is the role of those criteria scores, 1, 4, 3/4 in that example?
So that's a good point. Maybe that's a red herring. It's not really important. The only interesting thing is that they are completely symmetric. So you could have 1/3, 2/3, or 1/3, 1/2, and 1/2, 1/3. The only thing that I'll stress on here is that they are different. X1 is not equal to X2, and they're symmetric. That is, X2 is just the reverse of X1. There's nothing else. Yeah.
Okay, thank you.
Other questions? All right. So at least, as I said, this result was quite counterintuitive to us. But yeah, question. Please go ahead.
So is it like this result, like moving to the left, is because of the third axiom, the strategy proofing?
So thanks for the question. So this is actually only considering dominance. So here, in here, we said that let's not worry about the other axioms. Let's look at dominance. On the left-hand side, I kind of defined what we want under dominance. So we want that under these criteria and overall scores, we want f hat of x1 to be at least as much as f hat of x2. Now, on the right-hand side, what I'm just showing you is what happens if you try to run that optimization problem under the L21 loss. And it turns out, if you just use that L21 loss, you'll get a result which says that f hat of x1 is strictly smaller than f hat of x2. And that's completely independent of axioms. This part about this red box is just if you just run that earlier optimization problem under the L21 loss. And what we are arguing is that, hey, L21 loss is not a good idea because this red box is opposite to what we wanted in this blue box. Does that answer your question?
Yeah, now I get it. Thank you.
Great. Thank you. Other questions? Okay. So from these theoretical results, we now understand that if we like these axioms, then L11 loss is the only one possible. So now we tried this on real data. So we tried this on data from the IJCAI conference 2017. And what I'm about to show you is the following. So these are just some fun plots where on this data, we ran that optimization problem which I had shown you earlier under the L11 loss. And what I'm about to show you is some plots of how the learned mapping F hat looks like. Now, IJCAI had 5 criteria. I can't plot a 5-dimensional function, so I'm going to show you some representative cross sections. So first, there are 2 criteria.
Nihar, quick question. Could you just, what were these criteria or some of them just to have a big concrete?
Yes, I'll come into that. Yes.
Okay.
Yes, I'll tell you that. So 2 of the criteria were the writing quality and relevance. And we found that in the learned mapping, if any paper were really bad with respect to either of these criteria, then that was a significant downside for the paper. If it was really good, then it was appreciated. And in between, there was a big plateau where it was nearly irrelevant. Then 2 other criteria were the technical quality and significance. And both of them had a pretty high influence on the overall score. And this influence is approximately linear. And then the 5th and final criteria was originality, which had a moderate influence. So this completes the part on subjectivity. I'm very happy to take any more questions. All right, if there are not, then some open problems. So we looked at this problem from an axiomatic perspective, from a social choice theory perspective. And it's open and it's a very interesting problem of learning such a common mapping, thinking about it from statistical or information theoretic perspectives. Secondly, it's also interesting to consider mixture models where you have a seemingly homogeneous population of reviewers, but still there might be mixtures of different perspectives. And maybe you want to learn multiple F hats under this using a mixture model. These are some problems that I think are both theoretically and practically interesting. Now I'll move on to this problem of miscalibration. This is with Jingyan Wang.
So Nihar, so the goal here is to have a descriptive theory, or more also you would like to, like you learn the function F hat, you would like to use it maybe to make the reviewer process more fair, or
Yeah, absolutely. So you're talking about the general space of subjectivity, it not necessarily.
Yeah. I mean, or this area, I guess.
Yeah.
This sub area.
Yeah. So the goal is to make the process more fair, somewhat more efficient, and make it also somewhat more quantitative. So the issues of quote unquote fairness due to subjectivity, due to miscalibration, and other issues that I'll talk about are well noted in the literature, where most of this literature which calls out these issues are outside of engineering and computer science. And our goal is to use the tools that we have in order to impart fairness and more efficiency, etc., with strong guarantees.
I have a question just
Yes.
to make sure I didn't miss anything. So what you have learned is what is going to be the loss function, but do we know like what f going to be, which class f belong to?
Yes, very good. So now that we have learned, we know that we want to use L11 as the loss function. What we will do is that, let's say tomorrow suppose tomorrow you run a conference, then you get the reviews from the reviewer. So each review comprises criteria score and overall scores. And then we'll use this loss function to learn an f hat for your conference. And then this f hat will be used for all the reviews in your conference. So the learned f hat would depend on the data. Does that answer your question?
Yeah, okay, thank you. Yes.
Yeah,
Wait,
one more question,
please.
Nihar. So maybe you already answered this, but my question is, should we also be interested in other types of loss functions, like not the LPQ?
Yeah, so that's a good question. And more broadly, yes, there's a much broader possible class of loss functions. What we did was we looked at a few families which were prominent, and at least for reasons that I can discuss offline, but reasons having to do with the specific domain of reviewers, papers, and so on, LPQ was the most natural family. So there are others like based on the singular values or eigenvalues and so on, but we ruled them out for various other reasons and we focused on LPQ. But that said, yes, of course, our framework is restricted to this, and one could obviously consider things more broadly. Yes.
Okay, thanks.
Great. Other questions? Please ask. Okay, so let's talk about miscalibration. And miscalibration in ratings are a well-known issue. So by miscalibration, we mean that, say, your interpretation of a 5 out of 10 rating might be very different from my 5 out of 10. And this issue is well known in the literature. So Mitliagakis et al. Say that a raw rating of, say, 7 out of 10 without other information is potentially useless. Amar et al. Say that the rating scales and individual ratings are often arbitrary and inconsistent across people. And this landmark paper on rank boosting by Freund et al. Says that using rankings instead of ratings is very important because different people might use completely different ranges of scores to express identical preferences. Now, in the literature, there are two common approaches towards addressing these issues of miscalibration. One approach is to assume some simplified models for miscalibration. For example, that every person has some affine every person, when giving a rating, does some affine transformation with Gaussian noise. Now, algorithms based on these models were actually tried in some conferences, and they did not work well. A second approach is to use rankings. For example, when you get ratings, now you take the ratings given to all papers by a reviewer and then convert that to a ranking of all the papers by that reviewer. Or maybe you directly collect rankings. And using these rankings is commonly believed to be the best option if you can't really make such assumptions on miscalibration. Now, this is a folklore belief that it's the best option. And the key question that we ask here is that if, let's say, we don't want to make assumptions on how this miscalibration behaves, then is it possible to do better using ratings than converting the ratings to rankings? So let me formalize this, and in the interest of time, I'll use a simple setting which we call a canonical 2x2 setting. In this setting, we have 2 papers and 2 reviewers. Now the two papers, let's say they have some true score. So for the moment now, let's forget about criteria scores and overall scores. Let's just say there is this overall score, which is a true score for either of these papers. We'll call them Z star A and Z star B. Now we modeled the miscalibration of each reviewer in the following manner. So this first reviewer has some implicit function in their mind, which we call F1. And this is their miscalibration function. That is, if given a paper I, which has a true score Z star I, this reviewer, because of their own miscalibration, outputs F1 of Z star I. Likewise, the second reviewer has some miscalibration F2, which is a function in their mind. And given any paper I, which has a true score Z star I, they don't give Z star I, they output F2 of Z star I. F1 and F2 are not known to us. Z star A, Z star B are also not known to us. Okay, any questions so far? Okay. So now here's the setting. So we don't want to make much assumptions on miscalibration. The only assumption that we'll make is that F1 and F2 are strictly monotonic, strictly increasing. And there's no other assumptions on F1 and F2. And beyond this, we let an adversary choose these functions. So an adversary comes and chooses F1, F2. The adversary comes and chooses Z star A, Z star B. Now, we assume that one paper is assigned to each reviewer uniformly at random. So every reviewer reviews one paper. Every paper goes to one reviewer. And this assignment is done uniformly at random. So now the data that we have in this canonical 2x2 problem is the assignment of who reviewed which paper and the score given by each reviewer. So the first reviewer reviews one paper and gives a score. The second reviewer reviews one paper and gives a score for that. So this is the data that we have. And now the goal is to find if Z star A is greater than Z star B or if Z star B is greater than Z star A. Any questions? Please ask me questions since I'm going to ask you a question. Okay, then let me ask you a question. So towards this goal, let's for the moment suppose that instead of asking each reviewer for a score or rating, let's say we ask each reviewer to give a ranking of the papers that reviewer is reviewing. So we ask reviewer 1, hey, look at all the papers that you have and give us a total ranking of those papers. Likewise for reviewer 2. Note that each reviewer reviews just one paper. And if we are asking for rankings, then how well do you think we can do with respect to this goal of finding if A is better than B or vice versa? So each reviewer is reviewing exactly one paper. And now we are asking each reviewer to give a total ranking of all the papers that they are reviewing.
So how is it going to help, right? So it's not going to help.
That's a very good point. So eliciting rankings is vacuous, as Salim is saying. And hence, trying to answer the question of which paper is better is same as random guessing, that you can't really do better. So you'll have at most a probability half of being correct. Okay, great. Thank you, Salim. So let's see. The question is now that if we ask the reviewers for scores, but if they're completely miscalibrated, the adversary is allowed to choose these miscalibrations, then can we do strictly better than random guessing? And well, it turns out that if you consider deterministic estimators, then you can't do better. You'll be at probability of success half. However, more generally using intuitions from Stein's phenomenon and empirical base. And for this specific problem, a more concrete connection to Cover's envelope problem, turns out that you can strictly outperform random guessing through ratings, even though the miscalibration was chosen by an adversary. The estimator is simple enough, but I can discuss it offline if people are interested. So overall, what this suggests is that if you use ratings, you can do strictly better than rankings, even if the miscalibration is arbitrary or adversarial. And then this was a 2x2 setting, but we use this as a building block for more general settings as well. So here we made no assumptions at all. And previous literature, they make very strong parametric affine kinds of assumptions. And an important open problem here is the middle ground. That is, are there some nice non-parametric assumptions on which you can do something interesting that works well in practice and doesn't break down in theory? Moreover, as you saw that we discussed miscalibration and subjectivity independently, and a key open problem is to merge the two, because in practice, you'll have all of these occurring together. With this, I'm going to move on to other topics, but before that, I'll pause to see if there are any questions. Okay, I'll move on to the next three topics, and these are topics on which I'll be extremely brief, and I'll be very happy to chat offline about these. So the third topic we look at is the issue of biases. This is with Ivan Stelmach and Arti Singh. And there is a lot of debate in various scientific communities about biases associated to gender, race, fame, etc. of authors. Due to this, there is a lot of tension between two different kinds of peer review systems. Single blind, where the reviewers can see author identities, and double blind, where the reviewers cannot see the author identities on the submitted papers. Now, in this single blind versus double blind debate, there is often the question of, where is the evidence of bias in my research community? And this begs the important question of designing tests, rigorous tests for biases in the peer review process, while still ensuring a good review process. What do I mean by that? Well, so in a peer review, we can't do a completely randomized controlled trial. We can't necessarily just give each paper to a random reviewer and so on. So we want to ensure a good review process, but still be able to test. Towards this, we design an experimental methodology that does not require much change to peer review processes. We design statistical tests associated to it and provide strong statistical guarantees. So if, for example, in ISIT next year, which is currently single blind, we want to test if there exists such biases, we could use these tools in order to rigorously do these tests. I know I was extremely brief here, but if there are any questions, I'm very happy to answer.
So could you maybe explain or just summarize it in a few seconds? What's this experimental methodology?
Yeah, so the experimental methodology pertains to the following setting. So, and this is actually, well, our starting point was this amazing experiment done in the Wisdom Conference about 3 years back, where they split reviewers uniformly at random into two groups. They made one group a single blind group, the other group a double-blind group. Now, each paper was reviewed by 2 reviewers from the single-blind group and 2 reviewers from the double-blind group. And so they had amazing data. For each paper, they knew the attributes of the authors, and they knew how the scores are in the single-blind condition and how the scores are in the double-blind condition. And now using this data, they tried to test if there are actually biases in single blind versus double blind with respect to the gender or the fame, etc., of the authors.
Nihar, how about, I'm sorry, but one thing. So how about changing the authors? Like you could also manipulate the data to see, like putting some people's name on some other people's.
Yeah, so that's a good point. Unfortunately, that's far harder logistically. The reason being that you have to be extremely careful. Like if you have a paper and it has, let's say, my name on it, maybe people can guess that, yeah, it's probably not Nihar because he works on something else. So you have to be extremely careful. There are also various other logistical things, like you have to take permissions of the author of that paper and that other person, to replace the names and so on. And if I replace Salim El Royab with some unknown name, again, that's another confounding factor of not gender, but this already very well-known author versus unknown author and so on. So that's why they did, that's why perhaps they did this, that they directly tested single blind versus double blind. How does it look? So that was our starting point. And first we found out that there were various issues in their experimental methodology and statistical tests. Even though they split reviewers uniformly at random, like a randomized control trial and so on, some complexities in the peer review process breaks the tests. And here in our work, we say, hey, let's follow a slightly different methodology, and then you get strong guarantees and so on. Other questions? All right. Let me also talk about this issue of noise. This is also with Ivan and Aarti. And by noise, I'm specifically talking about poor reviews due to inappropriate choice of reviewers. Now, as some of you might know, most major machine learning and AI conferences use automated assignment algorithms to assign reviewers to papers. For example, the Toronto Paper Matching System, or TPMS. However, we can show that these matching systems are quite unfair, especially to interdisciplinary or niche papers. So the key question here is, how do you assign reviewers to papers, ensuring fairness and accuracy? And towards this, we design a new assignment algorithms which has strong theoretical guarantees. There was an independent evaluation of our algorithm by Cobren et al. In 3 top-tier conferences. And our algorithm was also tried and actually used in ICML 2020. And in all of these evaluations, we found that in terms of a standard fairness metric, our algorithm was much better than TPMS. And if you look at the objective which TPMS tried to optimize, our algorithm had a very similar value of that objective as the TPMS algorithm. So it was kind of a win-win situation. Any questions? I'm happy to chat offline. And one more issue that I'll talk about is that of strategic behavior. This is with Han Zhao, Yichang Xu, and Xiaofei Shi. And what do I mean by this? So if I am a reviewer for a conference, and if I've also submitted a paper to the conference, well, I'm incentivized to give a lower score to the papers that I'm reviewing, so that in a relative sense, the chances of my paper getting accepted go up. Now, empirically, these issues are quite well studied. And the question that we ask from a theoretical perspective is how to make peer review strategy proof. That is, if I'm a reviewer, any kind of manipulations that I do as a reviewer will not affect the decision for my paper. And in terms of results, we have a framework and some algorithms for strategy proofness. This works under some assumptions, and we have verified that these assumptions do work in data from past iClear conferences. And we also have some negative results on when it's not possible to be strategy proof. With that, so I'll stop here, and we're also doing some simple empirical research investigating the data in past conferences, etc. And I'll leave you with a graphic here. I'm very happy to take any more questions. Thank you so much.
Thanks a lot, Nihar, for a very nice and engaging talk. One question I have before also, I'll invite other people that are here to ask questions. I have a kind of a double question. One is that in general, what are your recommendations for conferences and for reviewers based on the data? Like you see, like what should we do, whether it's ISIT or other. And the other thing, many conferences has acceptance rate. Yeah. How does that? What I never understood as a reviewer myself, or TPC, I never understood what does that mean. So yeah, I would love to hear your thoughts on this.
Yeah, that's a very good point. So regarding acceptance rate, I think one classical explanation or justification for that is the fact that you are going to have this conference in a physical location, and there is limited room there. So there is limited room for presentations, there is limited room for posters, and hence you can have at most so many accepted papers. Now, at least I personally, and I've written things on these blogs as well, that I personally would prefer if the acceptance rate was increased, and let's say one chunk of papers was just accepted as papers with, let's say, either a video online or something like that. So I would prefer that, but that's the standard, that's previously the justification given. Another kind of justification for low acceptance rates is more of that we want it to be only very high quality, etc. That's still kind of fuzzy and debatable though. So I kind of agree with perhaps the concern that you're bringing out. In terms of recommendations, so especially for ISIT, at least I personally have a feeling that, you know, as looking into the machine learning conferences, like they're trying out a lot of new things. They're trying to keep improving, be more fair, you know, be more inclusive and so on. Whereas ISIT is not really changing, right? So maybe try to, you know, do some experiments to understand what's really happening. Are we representative or inclusive enough? Are we fair enough? And maybe try out different things. Yeah, like what ML, so ML is really open to all of these. And in fact, even this year, we've done some experiments at ICML 2020. We have obtained some very interesting insights onto the behavior of reviewers and reviews. And yeah, that will be out in about a month before the actual conference. So it'll be great if ISIT could, you know, maybe ISIT also does some more experimentation, etc.
Thanks, Nihar. I also agree. So I want to also, I think we asked lots of questions during the talk, but if someone has a question that wants to ask to Nihar right now, then please go ahead.
Yeah, I just want to thank him for this nice talk.
Yeah, thank you so much for attending and for your very nice questions.
Yeah, thanks a lot, Nihar. And I'm really happy that we had you give a talk here. It's a very interesting topic.
Yeah,
thanks again.
Thanks, Salim. Yeah. Thanks for the invitation.
Yeah. See everyone next time in the next channel talk.
Bye.
Bye-bye.
Thank you, Nihar. Thank you, Salim.
Thanks.